Okay, so in this challenge, we have been given a Docker file which installs QEMU on an Ubuntu machine and runs the challenge binary. Let's open the binary in GitHub and start reversing it. Immediately, we can see that it asks for a license key and passes it to some sort of format validation function. The function ensures that the license key is exactly 23 bytes and has a dash in every sixth character. The remaining characters may be numeric values or uppercase alphabets. Once the format is validated, the program creates a copy of the key, but this time without the separating dashes, so it's reduced to only 20 characters now. It will pass this new key to the actual check function, but more on that later. If the function validates the key, we automatically call win and decrypt something with the key. So our goal is to ensure that the validate function returns successfully. Let's have a look at it now. We can see that it runs a loop 4 times, and in each iteration it creates a QEMU command, writes some data to a temporary file, runs that file with QEMU and passes the license key as argument and compares the output to 0. If the program exited successfully, we repeat the process to finish the loop. However, if any one of the iteration returns a non-zero value, then we fail then and there itself. If you take a look at what data is being written to the temp file, you will see elf headers. This is what made the challenge so interesting. The program we are given contains within itself 4 different license check binaries of different architectures, which all need to be reverse engineered to find the correct key. We can simply use dd to extract all the 4 binaries. Let's start reversing the first one. We can see that it's a relatively small binary and uses some sorting algorithm to sort the input and compare it to a fixed known value. This means that any permutation of this known string will satisfy the binary. And this also means that we have found a character set for the key. Let's have a look at the second one now. It loops through the key and compares the sum of the numeric and alphabetical values to some hard-coded values in each group of the key. Basically, the first binary gave us the character set and the second one helped us identify which characters to place in which group. I gave this information to my teammate who very easily comes up with all possible keys. However, it's still too large to brute force, so let's continue with reversing. At this point, the third binary did not make any sense, so I ignored it and proceeded to the fourth one. The fourth and final one had 2 parts. The first one was relatively easy to understand, it was just leaking information about the key, and the second one again did not make any sense. From this information, we come to know that the 15th, 17th, and 18th characters must be Y, M, and 8 respectively. I update my teammate about the findings and he optimizes the script to narrow down the possible keys significantly. However, unfortunately, brute force was still not possible and reversing was too difficult, so we gave up and could not solve it. After the CTF was over, I talked with the author and gained confidence to give it another shot, particularly the third binary. I opened it in GitHub and here is what it does. It basically finds the location of the nth character of the key in another string and calls another function with the following arguments. The first one being some data address plus the position minus start of that string whole multiplied by 96, and the second being the next character, and the third is constant 24. Oh, by the way, the position minus start simplifies to the index of the nth character in the string. Anyway, so our goal is to ensure that this function returns 1. We can see that it can only happen when this if condition becomes true and the program breaks out of the while loop. That will happen when the next character is equal to the given data plus I times 4. And remember, our goal was to return 1. The function will return 1 for every value of I as long as it's less than 24. So a total of 24 possible successors are allowed. And this is a great improvement. This will significantly reduce the number of possibilities. We can now write a simple Python script to compute all possible successors for every character in our character set, and here is the result. If we integrate this within the brute force script, we can see that we have significantly lowered the amount of possibilities. And this itself contains a lot of duplicates for some reason. Anyway, after removing them, it's reduced to just half the size, which is a drastic change from where we started. And this is very well within the brute forceable limits. So after that, I quickly write a simple script to test all of these keys and eventually crack the license key after about 30 minutes of brute force. Obviously, with the correct key, we get our flag. And although I couldn't solve it during the CTF, the process was thoroughly enjoyable and getting the flag was very satisfactory. And yeah, that's it. Thanks for watching and see you next time.